Thank you for joining me on this adventure. Your presence means the world to me. It's a pleasure to have you join us as we uncover the secrets of Burnside's lemma. Burnside's lemma, sometimes also called Burnside's counting theorem, the Cauchy-Frobenius lemma, or the orbit counting theorem, is a result in group theory that is often useful in taking account of symmetry when counting mathematical objects. It was discovered by Augustin Louis Cauchy and Ferdinand Georg Frobenius, and became well known after William Burnside quoted it. The result enumerates orbits of a symmetry group acting on some objects. That is, it counts distinct objects, considering objects symmetric to each other as the same, or counting distinct objects up to a symmetry equivalence relation, or counting only objects in canonical form. For example, in describing possible organic compounds of certain type, one considers them up to spatial rotation symmetry. Different rotated drawings of a given molecule are chemically identical. However, mirror reflection might give a different compound. Formally, let G be a finite group that acts on a set X for each G in G. Let Xog denote the set of elements in X that are fixed by G left invariant by G, that is, Xog XX, GXX. Burnside's lemma asserts the following formula for the number of orbits, denoted Xig. Axig are fracog sum gin gaxig. Thus the number of orbits a natural number or is equal to the average number of points fixed by an element of G for an infinite group G. There is still a bijection. Gxid Gxog. As we transition to the next segment, let's unravel the mysteries surrounding necklaces and gain a fresh perspective. There are 8 possible bit strings of length 3, but tying together the string ends gives only 4 distinct two-colored necklaces of length 3, given by the canonical forms 0, 1, 11, 111. The other strings 110 are equivalent to 1 by rotation, while 110 and 101 are equivalent to 11. That is, rotation equivalence splits the set X of strings into 4 orbits, X, 10, 101. Earth Burnside formula uses the number of rotations, which is 3 including the null rotation, and the number of bit strings left unchanged by each rotation. All 8-bit vectors are unchanged by the null rotation, and 20 and 111 are unchanged by the other 2 rotations. Thus the number of orbits is $4 a frac. For length 4, there are 16 possible bit strings, 4 rotations. The null rotation leaves all 16 strings unchanged. The 1 rotation and 3 rotation each leave 2 strings unchanged, 0 and 11. The 2 rotation leaves 4 bit strings unchanged, 0, 101, 10, 11. The number of distinct necklaces is thus $6 a frac, represented by the canonical forms 0, 1, 11, 101, 111, 11. The general case of n bits and k colors is given by a necklace polynomial. As we progress through this video, let's now turn our gaze towards colorings of a cube. Burnside's lemma can compute the number of rotationally distinct colorings of the faces of a cube using 3 colors. Let X be the set of possible face color combinations that can be applied to a fixed cube, and let the rotation group G of the cube act on X by moving the colored faces. 2 colorings in X belong to the same orbit precisely when one is a rotation of the other. Rotationally distinct colorings correspond to group orbits, and can be found by counting the sizes of the fixed sets for the 24 elements of G, the colorings left unchanged by each rotation. The identity element fixes all colorings 6 90-degree face rotations, each fix colorings 3 180-degree face rotations, each fix colorings 8 120-degree vertex rotations, each fix colorings 6 180-degree edge rotations, each fix colorings. A detailed examination may be found here. The average fixed set size is thus: Axig of fracor left got plus got plus got plus got right equal. There are 57 rotationally distinct colorings of the faces of a cube in 3 colors. In general, the number of rotationally distinct colorings of the faces of a cube in n colors is A fracas left an n plus n a right. With the groundwork laid, let's now examine proof and its connections to our previous discussions. In the proof of Burnside's lemma, the first step is to re-express the sum over the group elements GG as an equivalent sum over the set of elements XX. Georg G, X G X G X X X Xerg X. Here Xerg XX, GXX is the set of points of X fixed by their element G of G, whereas GXGG, GXX is the stabilizer subgroup of G, consisting of those symmetries that fix the point XX. The orbit stabilizer theorem says that for each XX there is a natural bijection between the orbit GX, GG and the set of left cosets X. Lagrange's theorem implies that Gx ijid X. The sum may therefore be rewritten as sum x in xgx sum x in xdefracag.x equal sum x in xdefracag.x. Writing X as the disjoint union of its orbits in Xig gives sum x in xdefracag.x equal sum a in xig sum x in a frackia equal sum a in xig 1 equal ijdetic. Putting everything together gives the desired result. Georg G hexage. This is similar to the proof of the conjugacy class equation, which considers the conjugation action of G on itself, it is the case xg and gx1, so that the stabilizer of X is the centralizer gxzx. Our focus now turns to enumeration versus generation, an important aspect of our discussion. Burnside's lemma counts distinct objects, but it does not construct them. In general, combinatorial generation with isomorph rejection considers the symmetries of G on objects X, but instead of checking that GXX, it checks that GX has not already been generated. One way to accomplish this is by checking that GX is not lexicographically less than X, using the lexicographically least member of each equivalence class as the canonical form of the class. Counting the objects generated with such a technique can verify that Burnside's lemma was correctly applied. With our foundation established, it's time to explore history, the lemma that is not Burnside's, and its relevance to our overarching theme. William Burnside stated and proved this lemma in his 1897 book on finite groups, attributing it to. But even prior to Frobenius, the formula was known to Cauchy in 1845. Consequently, this lemma is sometimes referred to as the lemma that is not Burnside's. Misnaming scientific discoveries is referred to as Stigler's law of eponymy. I hope you learned something new today. Let me know what you found most interesting in the comments below.